we are going to use something called an ice table to keep track of the initial change in equilibrium concentrations in an equilibrium system. So this helps us keep track of everything that's going on in our problem. So let's take a look into the problem and see how we would use an ice table to keep track of the initial concentration, the change in concentration, as well as the equilibrium concentration. So here we have an equilibrium system, and it's established in a 1.00 liter flask at 25 degrees Celsius, and it's represented by this equation below right here. We're told that initially there's 1.05 millimoles per liter of H2 and I2, and at equilibrium the concentration of I2 drops down to 0.25 millimoles per liter. And we're asked, what is the equilibrium constant for this system at equilibrium? And this is where we're going to use an ice table. So what we do is we write down what we have as reactants, and they go in the top columns right here. So H2, I2, and hydrogen iodide. And then we're going to write down the initial, the change, and the equilibrium. And you can see that spells ice. So we're going to write down from our problem, we know what our concentration initially is of the hydrogen gas and the iodine gas. And we just write these down in our table. Then we're told that at equilibrium, the concentration of iodine gas is 0.25 millimoles per liter. So I'm going to write that down right here because this represents what it is, the concentration at equilibrium. Now, using the initial concentration and the equilibrium concentration, it's possible to calculate what this change value is. And what you need to do is just take 1.05, subtract 0.25, this, subtract this, and we see a change of negative 0.80. That's what I put into the table for the change column. And then when you're doing ice tables and using ice tables, you have to have a balanced chemical equation to understand what exactly is going on with our chemical system here. So I know that I have 1 mole of iodine gas reacting with 1 mole of hydrogen gas. So if this changed by 0.80, this is also going to change by 0.80. Therefore, at equilibrium, I can just take this, subtract this, and I'm going to get the same value at equilibrium. The next thing we need to do is we need to figure out what our concentration of HI is. We know that at the start of our reaction, we didn't have any hydrogen iodide produced because we only had the hydrogen and the iodine initially. So its initial concentration is 0. Then we're going to use molar ratios once again to figure out what is the change in the hydrogen iodide. So we know that we had 0.80 a change for iodine gas. And we know that for every 1 mole of iodine, we have 2 moles of hydrogen iodide produced, that 2 coming from the coefficient that's in this term. So therefore, this must have a change of positive 1.60. So if we figure out what this difference is, we see that we now have an equilibrium concentration of 1.60. And the reason we needed to calculate all these equilibrium concentrations is that allows us to calculate what our Kc value is, or our equilibrium constant. So we know that Kc is equal to this expression here. And for our example, we see that all of the species present here are in gaseous state, so they're all going to be included in our equilibrium expression. The 2 right here, we have to take account of that, and that becomes an exponent in this expression, right here. So this has an exponent of 1. These just have coefficients of 1, so they don't have an exponent, or they're just exponent is 1. Then what we do is we use our ice table and substitute our values for the equilibrium concentrations into this formula, and we can figure out what the equilibrium constant is. We see that right here, this value here is 40. It's much above 10, so we see that this is a quantitative reaction in this case, and that we're mostly going to be producing Kc.